Welcome to Science for Sleep, where wonder and calm meet. Each night we drift through galaxies, oceans, and mysteries of the natural world, not to startle, but to soothe. So, take a deep breath. Let curiosity slow your thoughts and fall asleep to the sound of discovery. Point Nemo, drifting to the loneliest coordinates on Earth. There is a place in the ocean where, if you were floating on the surface, the nearest solid ground in any direction would be over 2,500 kilometers away. No shoreline, no lighthouse, no island rising on the horizon. Just a perfect ring of water and sky. That point is called Point Nemo, the oceanic pole of inaccessibility. And it lies in the southern Pacific Ocean, far from the busy shipping lanes, far from coastal fishing grounds, far from almost everything that usually connects the sea to human life. Its coordinates, calculated by a cartographer with a computer rather than a ship with a compass, fall at about 48 degrees 52 minutes south, 123 degrees 23 minutes west, anchored not to land, but to geometry. Point Nemo is not special because of what you see there, but because of what you don't. There is no island marking the spot, no buoy permanently bobbing to announce it. The seafloor beneath lies roughly 3,700 meters down, a quiet, abyssal plain in the South Pacific Ocean gyre. A vast rotating system of currents that circles slowly and keeps nutrient-rich waters at a distance. The three nearest pieces of land are all tiny and remote themselves. Ducie Island, part of the Pitcairn Group, Motu Nui, a small islet near Easter Island, and Maher Island, close to the fringe of Antarctica. Each lies about 2,288 to 2,700 kilometers away from the point, so far that none of them are visible from the surface. When you stand mentally at Point Nemo, land becomes an abstract idea rather than a visible reassurance. The name Nemo is a layered nod to absence. In Latin, Nemo means no one, a fitting label for a place where humans almost never are. It is also a tribute to Captain Nemo, the reclusive submarine commander from Jules Verne's novel 20,000 Leagues Under the Sea, who roamed remote and unvisited stretches of ocean in his vessel, the Nautilus. The idea that the farthest point from land on Earth would carry a name tied to fiction feels appropriate. Point Nemo lives partly in science and partly in imagination, a coordinate that exists on charts and computers, and in stories whispered about the middle of nowhere. Unlike mountain summits or polar caps, Point Nemo was not discovered by a rugged expedition battling ice and wind. It was discovered in 1992 by Hrvoje Lukatela, a Croatian-Canadian engineer who used a geospatial program and the WGS-84 reference system to search, mathematically, for the ocean location farthest from any coastline. He fed the outline of Earth's continents and islands into a computer, then let an algorithm iterate through possibilities until it located the point maximizing distance from land. The result was a coordinate in the South Pacific that no one had ever sailed to on purpose, but which had quietly existed for millions of years, unnoticed, following Earth through its orbit around the sun. To appreciate how isolated Point Nemo is, it helps to consider scale. A commercial airliner cruising at altitude could cross the entire Atlantic Ocean in the time it would take a ship to steam from Point Nemo to the nearest speck of land. The closest coastline lies over 1,600 miles away. Even fast vessels take days to cover such distance. For much of the time, the nearest humans to Point Nemo are not at sea level but overhead. Astronauts orbiting in the International Space Station, only a few hundred kilometers above Earth's surface, are often physically closer to the point than people on land are. It is one of the rare places where space feels nearer than shore. This remoteness has practical consequences. Commercial shipping routes, which tend to connect populated coasts and major ports, arc far to the north and west of Point Nemo, leaving the region with very little vessel traffic. Fishing fleets rarely linger here either. The South Pacific Gyre that encloses the point is an area where upwelling is weak and nutrients are scarce, so surface productivity is low compared to the rich coastal upwelling zones off Chile, Peru, or New Zealand. Oceanographers sometimes describe the region as a biological desert at the surface. There is life, but it is sparse, and large shoals or dense blooms are rare. The quiet at Point Nemo is ecological as well as human. Because there are so few ships and so little life near the surface, the region around Point Nemo has been chosen as a kind of planetary disposal ground for machinery returning from space. It sits within what agencies sometimes call the South Pacific Ocean uninhabited area. And over the past decades, space organizations have guided more than 200 defunct satellites, cargo craft, and station fragments to burn up in the atmosphere and splash down in this remote patch of sea. The remains of Russia's Mir space station, multiple cargo vehicles, and countless smaller pieces of hardware now rest on the seafloor not far from the coordinate, forming an invisible spacecraft cemetery. In the early 2030s, current plans call for the International Space Station, one of the most complex structures humans have ever assembled, to end its life here as well, its surviving fragments sinking into the same dark water. Yet even this use as a graveyard does not much disturb the surface impression one would have drifting above. The re-entries are controlled, infrequent, and spread over time. Pieces that survive the fiery fall plunge quickly through the water column and come to rest on sediments thousands of meters down. There are no visible markers of this history, no floating debris field, no cluster of buoys or warning beacons. The ocean is efficient at hiding what it accepts. To a satellite camera, the region appears as a seamless expanse of deep blue, a circle of ocean surrounded by curving lines connecting that central point with its 3 nearest islands. If we stay at the surface and let our thoughts move slowly instead of our bodies, the most immediate presence at Point Nemo is the water itself. The South Pacific at these latitudes is influenced by large-scale wind patterns and currents that form part of the subtropical gyre, circulating clockwise in the southern hemisphere. Water here tends to be older, having traveled long distances from upwelling regions and gradually lost much of its nutrient load along the way. This makes the upper layers unusually clear. Sunlight can penetrate relatively deeply into the top few dozen meters, but has little organic matter to scatter off or feed. Beneath that thin-lit skin, the familiar descent into twilight and then darkness begins, the same layered dimming seen throughout the open ocean. But here it unfolds in a setting where very few eyes ever watch it directly. We can imagine lowering a sensor through the water, temperature sliding gently downward from the mid-teens at the surface to single digits. Salinity steady, oxygen changing with depth as it follows the memory of where the water last touched the atmosphere. That descent would pass through the mesopelagic twilight zone, then into the bathypelagic darkness, until at last the instrument reached the abyssal plain beneath, a flat sediment floor shaped by millions of years of slow particle rain. Microbial communities, tiny invertebrates, and occasionally larger wandering deep sea animals would inhabit those depths. But the impression would be of vastness, not density. The spacecraft remains resting there, join a landscape already defined by slow processes rather than sudden events. Point Nemo has also become a magnet for stories and speculation, simply because human imagination dislikes gaps. Its distance from coasts and ships makes it an ideal setting for fiction. Fans of H.P. Lovecraft often note that the coordinates he gave for the sunken city of Raleigh in The Call of Cthulhu fall not far from the real-world location now known as Point Nemo. An eerie coincidence that encourages talk of hidden structures or ancient things sleeping beneath the waves. In the late 1990s, a powerful low-frequency sound. Nicknamed the Bloopy, was detected by hydrophones in the southeastern Pacific and roughly triangulated to a location within the same general region, prompting widespread speculation about unknown giant creatures. Later analyses concluded that the sound most likely came from ice-related processes, like cracking or calving, rather than biology. But the idea that the middle of the ocean might harbor something vast still lingers in popular culture. Science, though, tends to paint the area around Point Nemo as quiet rather than monstrous. Oceanographers use the region as a natural laboratory for studying low-productivity gyre dynamics, long-range pollutant transport, and the background noise of the ocean recorded by hydrophone arrays. When they refer to it as empty, they mean it statistically. Fewer organisms per cubic meter, fewer ships per year, fewer direct measurements compared to busier or richer seas. For the purposes of a calm documentary, that statistical emptiness becomes an emotional spaciousness, room to think about how the planet is structured, about the concept of middle in a world mostly covered by water, and about how a coordinate can be both real and abstract at the same time. Point Nemo is, in a way, a kind of mirror. It reflects how our perspective on Earth has changed. Before the age of satellites and global mapping, the idea of knowing the exact, most remote spot in the ocean would have been more poetic than practical. Now we can calculate it precisely, use it for orbital mechanics, worry about the environmental implications of sinking space hardware there, and tie it to literary references and internet myths. But none of that changes the experience that would greet a person actually floating at those coordinates. There would still be only the circle of the horizon, the gentle curve of swells lifting and falling, the sky above, and the knowledge that every shoreline is far away. Point Nemo here is not violent or noisy. It is simply remote. For a channel devoted to calm, faceless storytelling, Point Nemo offers a subject where the drama lives in the numbers and the imagination, rather than in footage of action. The script can linger on distance, on orbits converging overhead, on the slow fall of decommissioned spacecraft into quiet water, on the idea of astronauts looking down at a point that no one sails across routinely. It is a place where the phrase, "dead center of the ocean," does not mean lifeless, but unused, a coordinate that belongs more to the planet itself than to us. And it is only the beginning. Around this spot, currents, gyres, deep sea plains, and human decisions all play their long, unhurried roles, inviting us to keep drifting outward in the next chapters of the story. Deep center does not mean deep silence, the hidden ocean beneath a remote coordinate. This documentary continues where isolation becomes not a visual emptiness, but a conceptual lens for understanding how much of the planet operates beyond direct human perception. Point Nemo sits in the southern Pacific, in the calm rotative grip of the South Pacific Gyre, a current system that circulates in enormous clockwise loops for thousands of kilometers, quietly carrying water that has traveled far from coasts, upwelling systems, and surface turbulence. Hollywood frames isolation as abandonment, but ocean biology frames isolation as redistribution. Even in the remotest coordinates, the water column remains occupied, interconnected, and consequential, layered with life that is sparse by surface statistics, but vast by planetary mass, and threaded into a physical system that protects calm rather than dramatizes it. At the surface, vessel traffic is almost non-existent compared to global shipping corridors, and surface phytoplankton blooms are lower density than coastal upwelling zones. But below that thin blue skin, life increases in scale, metric through replication and pressure arithmetic. The twilight zone, mesopelagic, beginning at 200 meters, still sees daily migrations of lanternfish and bristlemouth microswarms farther upward into sensory detection plumes, while zooplankton like copepods, euphausid krill intermediates, and larvacean colonies participate in the slow biological carbon pump, feeding on surface productivity above, then digesting at depth to exhale carbon into deeper water corridors. The deep scattering layer, a sonar-detected biological mass reflecting sound uniformly enough to once be mistaken for a seafloor, is part of this zone's identity, confirming that density here is an informational phenomenon, not an emotional one. The animals of the mesopelagic around Point Nemo adapt as though designed by the water's arithmetic itself. Gas cavities are metabolically minimized or entirely removed because gases compress unpredictably under pressure, and unpredictability wastes energy. Many fish here regulate buoyancy instead through oil-rich lipid deposition, soft cartilage emphasizing stability over skeleton rigidity, and pressure-compatible fluid dynamics. The ocean's temperature here drops gradually, hovering between 4 and 8 degrees Celsius in most layers, a constancy independent of surface seasons. Even the currents themselves conduct information calmly. The SOFAR channel, an acoustic corridor often located around 601,000 meters, carries whale song in low-frequency pulses across nearly entire basins, allowing sound to travel farther than the animals producing it need to know about visually. This is not silence, but sustainable communication bandwidth. Food arrives not always through ascension, but through passive descent. Marine snow particles, clumped organic material aggregated by bacteria, bit protein clusters, micro shellfall, silica plankton shells, and general detritus matter drift downward slowly through the zone, swirled occasionally upward by internal waves, but never rising into alimentary tornadoes. This particulate cascade feeds filter feeders like larvaceans who build mucus filtration houses that trap particles, then detach them calmly when clogged to let them sink again. The ocean teaches documentaries a different rhythm here. Engagement through the beauty of scale and contradiction instead of suspense-pacing spikes. Below the mesopelagic lies the bathypelagic and abyssal plain around 3,700 meters beneath Point Nemo, hosting microbial communities, scavenging amphipods, pressure-tolerant squid, and occasional deep-sea wanderers. But human exploration is minimal by footprint, conducted almost entirely by ROVs, controlled submersible light interview windows, and sonar scanning pulses instead of conquest. The region even became a chosen spacecraft cemetery, not because it is lifeless, but because it is unused by the biosphere the way we use the surface. An inheritance of space, rather than a battleground of motion. The largest narrative truth of this zone is that animals here survive not by aggression, but by calculated calm, unhurried migration scheduling, soft structural design, counter-illumination in faint blue wavelengths, pressure-wake sensory interception, chemical trail gradient reading, and gravity inheritance feeding that does not break the calm. Surface emptiness, deep arithmetic, the ecology of a place, far from shores. This documentary continues its exploration of Point Nemo by stepping away from the surface assumption that isolation equals lifelessness. The surface ocean around Point Nemo is often described scientifically as low in productivity, because it sits deep inside the South Pacific Gyre, a massive rotating system of currents where nutrient-rich upwellings from continental shelves do not arrive frequently. And phytoplankton densities are lower than those found in coastal zones fertilized by cold nutrient plumes. But below 200 meters, this habitat shifts from surface statistical sparsity into deep ecological arithmetic, where scale emerges through repetition, pressure adapts bodies calmly, and life spreads vertically without sonic congestion. The intrigue of Point Nemo is built not on visible crowds, but on the mathematics of distribution that governs its oxygen, biomass, prey cycles, predator patrol depths, and ecological endurance. The animals that inhabit the mesopelagic layers above Point Nemo do not swim dramatically across large horizontal axes like pelagic sharks or surface hunting fleets. Many of them drift, hover, or migrate vertically according to inherited biological clocks, moving in slow, repeating increments across a vertical ladder hundreds of meters tall. Lanternfish schools ascend toward 200-400 meters nightly to intercept feeding corridors, then sink back down before dawn without producing visible turbulence. Bristlemouths, the most numerous vertebrate genus in the ocean by estimated global count, spill upward into these twilight layers as well. Small-bodied, pressure-compatible, low skeletal density fish that thrive through replication rather than individual motion urgency, existing in numbers that range by estimate from hundreds of trillions to possibly quadrillions of individuals globally, though each individual is only a few centimeters long. These fish form the reflective acoustic layers that sonar once mistook for geological seabeds, because reflectivity at depth is a density function, not a dramatic soundscape. Food descends constantly from surface productivity above coasts thousands of kilometers away. Marine snow becomes one of the main nutrition sources intercepted by the mesopelagic biodiversity around Point Nemo. Flakes of organic particulate matter, including dead or dying plankton, bacterial-bound protein clusters, microscopic calcium shell fragments, chitin residue from molted crustacean exoskeletons, silica carapace dust, and distributed fecal pellets sinking slowly through the water column, sometimes for hours, sometimes for weeks, buoyed briefly by internal waves before gently settling farther down the pressure ladder. These particles do not fall in dramatic flurries like snowstorms. They fall like deep time, constant, passive, undramatic, rarely synchronized, enabling documentaries to sustain engagement through fact rather than sensory spikes. Larvaceans build and discard mucus-feeding houses that trap these particles, detach them without struggle when clogged, allowing the empty optical impression of open water to remain undisturbed while ecological consequence sinks invisibly downward. Oxygen cycling mirrors this calm inheritance. Surface oxygen dissolves into deeper currents not by atmospheric intrusion, but by density-driven sinking, especially from polar zones where cold, oxygen-rich water plunges downward due to temperature salinity density arithmetic before traveling across basins as deep currents. Point Nemo receives oxygen indirectly via these long, slow global pathways. This means oxygen levels at depth are not uniform, not alarming, not depleted to panic pacing, but redistributed into gradients that life evolved around patiently. Some twilight species thrive in oxygen minimum interfaces by evolving tolerant metabolisms, reduced motion budgets, or filament-based chemical interceptive feeding rather than aggressive sprints. This zone also reveals the calm behavioral psychology of predators fine-tuned to scarcity. Dragonfish patrol the deeper half of the mesopelagic during daylight, sometimes 1,500 meters down, rising upward at night to intercept vertical migration prey corridors. They dangle faint blue lures, glowing not in staccato flashes, but in short, low-intensity blinks that act like quiet questions asked into the dark. Hatchetfish glow their bellies faintly too, adopting counter-illumination that matches ambient blue moon-shifted overhead wavelengths to dissolve silhouette outlines for camouflage or prey interception without tempo aggression. Squids drift nearby, sensing chemical trails or pressure wakes left by vertical migration corridors, moving efficiently when interception triggers rather than chasing visually into scene violence. Even crustaceans that hunt smaller larvae or microzooplankton deploy sensorial precision instead of metabolic frenzy. The ocean floor below this zone, thousands of meters down, contains seamounts, ridges, abyssal sediment plains. hydrothermal vent corrugations that supply geothermal energy for chemosynthetic life communities. But we do not dive into those layers loudly. What matters for this documentary is to underline a quieter truth. Isolation shapes arithmetic calm, life scales through replication. Ecosystems intercept passively. Predators hunt by detection, not chase. Carbon is pumped downward like deep time. Oxygen enters by density corridors, not storms. Color vanishes, but identity remains coded. Sonar reveals scale, but not noise. And motion lives as inherited schedules instead of panic. Creating content that can inform without audience overstimulation. The geography of water, not land. How remoteness is measured in the sea. Point Nemo exists because geography is not only horizontal, but relational. Its remoteness is defined not by what occupies the coordinate, but by the geometry that surrounds it. The zone sits in the southern Pacific Ocean, far enough from land that even the closest specks of solid Earth feel more like footnotes than neighbors. This documentary segment begins with that principle. A quiet mental camera turned toward isolation as measurement, not loneliness as emotion. The concept behind Point Nemo comes from a field called the oceanic pole of inaccessibility, a classification that defines a point on Earth's surface that is farthest from any coastline in all directions. Point Nemo holds the world record for this. The nearest land masses to it are Ducie Island, Easter Island's small offshore islets, and Maher Island near Antarctica, all roughly equidistant, forming a triangle of extreme isolation around the coordinate. This triangle measures out to about 2,688 kilometers from the center, depending on reference calculations and rounding variations. It is the most remote surface coordinate on Earth's sphere when coastlines are plotted mathematically. But this remoteness was not found by seafarers shouting into storms. It was found by a computer tracing outlines quietly. Algorithms do not dramatize denies. They iterate. And they iterated until there it was. A quiet point maximizing distance from shore. Unlike continents shaped by geology and political borders, the Pacific around Point Nemo is defined by subtler boundaries. Gyres, currents, thermoclines, haloclines, pressure columns, oxygen gradients, and migratory depth ladders that bring enormous process without bringing loudness. The Southern Pacific Current System, the South Pacific Gyre, circles clockwise slowly due to the rotating forces of the Coriolis effect meeting wind-driven surface inheritance. But even the currents that birth this gyre move calmly across thousands of kilometers. They do not suddenly twist or erupt violently downward into the mesopelagic. Instead, they form a broad horizontal rotation that creates clearer surface water, because nutrient plumes rarely break into its central territory. This gives the documentary a tone that is naturally calm, because the region's vastness does not crowd motion into urgent turbulence. To understand its lack of surface productivity does not require a dramatic moral, only a calm explanation. Gyres hold low nutrient upwelling, which lowers phytoplankton bloom density compared with coastal zones. But low bloom density does not equal low life density at depth. It simply equalizes to minimal optical chaos. When surface waters are less crowded with algae, protein clusters, sediment runoff, or microorganism blooms, the upper layer remains unusually clear to the human viewer, creating a calming reception field. But below 200 meters, the water column is not empty. It is inhabited by billions more creatures than ships. This zone hosts migrators who rise and fall each night according to maps built not by landmarks, but pressure gradients and blue light sequencing. Many species read pressure wakes through lateral lines, identifying migration corridors rather than horizontal coastlines for navigation. Copepods drift upward nightly, tens of thousands of times their length without sound signature. Lanternfish ascend similarly, like silver streams at night, not bumping into each other dramatically, not creating turbulence, only creating biomass. Even for filmmakers, understanding geography here means understanding shifts in scale, not shifts in emotion cadence. Your documentary script should model this balance. Conceptually engaging by scale contradiction, emotionally calm by cadence. Eyes detect silhouette contrast upward. Bodies deposit lipid buoyancy quietly. Currents rotate slowly horizontally, but do not spike downward turbulence. Hunger is shaped by gravity inheritance, not violent upwellings. Reproduction is coded instead of dramatized by color. And geography exists as relational arithmetic instead of territorial border arcs. This is the physical psychology of the mesopelagic that invites calm infotainment without overstimulation. A faceless documentary narrator becomes especially appropriate here because there is no visible presenter needed to contextualize the location. The location itself becomes the presenter. The subject does not need an expressive human face. It needs geometry and physics. When speaking of a depth that is globally consequential, yet minimally visually intrusive, storytelling without a face becomes natural, not artificial. Point Nemo thus serves as a reminder that remoteness is not horror or emptiness. It is a geometric statement. It is a world where geography is measured quietly through distance from coastlines, but lived loudly through biomass at depth. For documentaries intended for calm reception, engagement emerges not through tempo spikes, but conceptual scale. Every remote coordinate has a story, but Point Nemo's story is written partly in space, partly in sea, and partly in choice. The documentary segment opens gently on the principle that a zone unused regularly by ships can be used gently by satellites returning from orbit, a timeline of consequence without loud, emotional pacing. Point Nemo lies within the South Pacific Ocean, uninhabited area. An oceanic center so distant from continents that it was selected as the safest region to guide spacecraft toward when their lives end. Unlike falling stars that burn silently without intention, these falling machines were guided with precision. Satellites, station fragments, cargo craft, and decommissioned space infrastructure is often deorbited into this region because no permanent population centers operate nearby under normal conditions. Space agencies treat this area not as a void, but as a safe impact minimizer because maritime vessel traffic is low in frequency and predictable in distribution. Because of this, more than 250 objects have ended their descent here historically, although almost none of it leaves stable surface signatures. They burn up high in the atmosphere, any surviving fragments falling quickly through upper layers and sinking toward abyssal plains thousands of meters down. These objects descend not like bombs, but like timed trajectories, infrequent enough not to create suspense arcs for calm viewers, consequential enough to inspire curiosity by abstraction. Even though the surface looks biologically empty statistically, the seafloor 3,700 meters down is already a sedimented archive. When satellite fragments settle there, they do not form chaotic debris clouds. They join sediments composed of billions of years of marine snow fallback, calcium shell dust, silica particulate fields accumulated slowly through pressure columns, and decomposed biomass residue that does not spike microbial panic pacing. The seafloor is quiet, oxygen present but transitional, motion non-existent by design. The ocean accepts what it is given without tempo spikes. But the sky above is not empty. Ironically, astronauts aboard the ISS are often closer to the point than land dwellers are, watching not through a camera host, but orbital glass, passing overhead every 90 minutes. The ISS circles contrast the point's isolation without creating jarring documentary suspense rhythms, because orbiting is predictable by physics as well. Astronauts have described the ocean from orbit as seamless blue, cloud-capped and borderless, swirling faintly like watercolor passes across immense horizontal distance. The narration can note this without stirring intensity. Below the very top, this band is threaded by the world's faintest but most enduring acoustic corridor, the SOFAR channel. Whale calls travel calmly at 601,000 meters, their low frequencies stretched like tonal grammar lines rather than spiked audible orchestra alerts, reinforcing a habitat that feels calm even when described as consequential. Beneath that, the twilight zone hosts the creatures this documentary niche respects most: lanternfish schools expanding into depth without turbulence roars, squid interceptive pulses deploying rarely like metabolic arithmetic, amphipods scavenging sediments, copepods drifting upward toward food corridors and sinking again before dawn without sonic splash patterns, jellies pulsing via cilia that refract faint ambient blue instead of emitting alerting optical fireworks, larvaceans constructing mucus filter houses that trap falling debris quietly before shedding them calmly downward again. What makes this zone engaging for documentaries is not violence or tempo shock, but planetary manuscript contradiction, empty optically by day, full instrumentally by senses, active metabolically by night, but not turbulent, remote relationally by geography, but visited overhead by orbit mechanics, more often than by sea-level human traffic. The story of Point Nemo became the story of documentaries where engagement emerges from scale and subtraction, not cadence spikes. A filmmaker creating a faceless channel can exploit this narrative gift by keeping visual palettes in blue-black gradient calm, transitions slow, facts consequential but delivered evenly, suspense non-violent in language, ascension non-frantic as motion explanation, carbon pump explained as a cycle not panic, reproduction noted as coded blinks not fireworks pacing, predators described as interception not chase, narration calm not alarm pacing, hostless by intention not deficiency. Between twilight and blackness, the hidden midwaters beneath Point Nemo. When you stand, in your imagination, at the surface of Point Nemo and look down, it is easy to think of the water below as one continuous emptiness. In reality, it is layered, and the layers between the dim blue of the twilight zone and the full darkness of the abyss are where much of the hidden life at the dead center of the ocean quietly moves. From roughly 200 meters down to about 1,000 meters, the mesopelagic, or twilight zone, still carries a faint memory of sunlight as a ghostly blue. Below that, the bathypelagic, often called the midnight zone, stretches to 4,000 meters and beyond, a realm with no natural light at all, only the occasional living glimmer of bioluminescence. Under Point Nemo, this vertical path is uninterrupted by continental slopes or coastal shelves. The water simply deepens, and with depth, biology changes its rules. Just below the sunlit skin above Point Nemo, the twilight zone continues much like it does in other open ocean gyres, but here it feels especially undisturbed. Lanternfish and bristlemouths, those small, silver, soft-bodied fish that dominate midwater biomass, rise and fall in huge numbers each night, performing the same diel vertical migration that happens around the globe. But here it occurs far from the noise of busy shipping lanes and coastal fisheries. During the day, they remain hundreds of meters down, resting and feeding sparingly on drifting plankton and marine snow, their bodies dotted with tiny light organs arranged in patterns that identify species and help them blend into the faint light from above. At night, as the surface dims, they drift upward, sometimes covering several hundred meters in an invisible elevator of life to feed on the slightly richer plankton world nearer the surface, before sinking back down again before dawn. It is all happening beneath a point on the map that we call empty. Between about 1,000 and 3,000 meters under Point Nemo, the ocean becomes truly lightless. This midnight zone, the bathypelagic, is where the character of life shifts from partial reliance on vision to almost full dependence on other senses. Here, the water is cold, typically just a few degrees above freezing, and pressure increases by 1 atmosphere every 10 meters, reaching hundreds of atmospheres by the time you are several kilometers down. Animals in this region have no need for the bright colors or complex patterns of shallow coral reef life. Instead, they are often black or transparent, built with soft, compressible bodies that accept the pressure and conserve energy. They rely heavily on smell, vibration, and the slight electrical fields produced by other living things, and, when needed, brief flashes of bioluminescent light. Under Point Nemo, this dark zone is probably less crowded than similar depths beneath productive coasts, because less organic material rains down from above. But it is still far from lifeless. Marine snow that began its journey near distant coasts or in far-off upwelling regions continues sinking through this column, slowly breaking up and being consumed by microbes and small animals as it falls. Occasionally, larger pieces of organic matter make the descent. The body of a dead fish, a jelly, or, more rarely, the carcass of a whale that has died and sunk far from land. When such a large food source arrives on its way down, it is intercepted by a succession of mid-water scavengers. Deep sea sharks, rat tails, amphipods, and other opportunists detect the chemical plume of decay and move toward it, feeding until it either disintegrates or continues downward to the seafloor. These events are infrequent, and between them, life here persists in a state of quiet conservation. Among the more striking inhabitants of these depths are the classic deep-sea predators. Dragonfish with long bodies and hinged jaws studded with teeth that look too large for their slender heads. Loose jaws with mouths capable of opening wide while keeping their silhouettes narrow. And various anglerfish that use a glowing lure to attract curious prey toward their waiting teeth. The light they produce is not showy. It is targeted, a small blue or green point, just bright enough to be seen at a short distance. Many of these fish also possess light organs along their bodies that act as counter-illumination, helping them match whatever faint glow might still drift down from above, so that from below, they disappear against the sparse light. In the waters beneath Point Nemo, these adaptations are doing their quiet work every night. Unseen by people, but necessary for survival, in a habitat where food is sparse and wasting energy on unnecessary movement can be fatal. Jellies and related gelatinous organisms also drift through the mid-waters here, forming an often overlooked component of the deep sea beneath Point Nemo. Some are simple, bell-shaped jellyfish slowly pulsing as they ride currents. Others belong to groups like siphonophores and satenophores, colonial or comb-bearing creatures that can reach extraordinary lengths. Many of them produce gentle bioluminescent flashes when disturbed, a soft, shimmering response rather than an explosive display. These faint flashes help confuse predators, attract mates, or simply warn others. In the almost total darkness, even a small spark of light carries information. Yet even with all these points of light, the overall impression remains one of calm, deep blackness, with most of the water column simply existing, cold and stable. The physical environment keeps this calm. Storms that churn the surface above Point Nemo do not penetrate this far down. Wind-driven waves and surface currents lose their energy in the upper few hundred meters, Below, the water moves more like a slow river, driven by vast global circulation patterns that respond to temperature and salinity differences across the whole planet. These deep currents pass under Point Nemo as part of their journeys, carrying with them water that may not have seen the surface in hundreds of years. Temperature changes slowly, not from season to season, but over centuries and millennia as circulation patterns shift. When we talk about the dead center of the ocean, it is easy to imagine a place cut off from the rest. But in reality, the deep water here is connected, just on timescales that are longer than human lives. That slow pace is mirrored in the lives of the animals. Many deep sea fish grow slowly, reproduce occasionally, and can live for decades. Their metabolisms are tuned to the low temperature and scarcity of food, and their hunting strategies are based on patience. A dragonfish may drift for long intervals, waiting for a vibration or a faint chemical cue to indicate that something edible is approaching. A deep squid may extend long filaments into the water, letting them act as invisible nets for passing prey. Even the predators seldom dash unless the odds are in their favor. There is almost nothing rushed down here, just the steady, patient continuation of life in a place that most maps mark only with a dot and a name. The mid-waters beneath Point Nemo, from the fading twilight zone into the midnight band, hold no cities, no sunken temples, no legendary monsters that science can confirm. What they hide instead is subtler, but just as remarkable. An entire vertical community built on the balance between very little energy and vast space. The complexity is easy to overlook from above, where only a coordinate is printed. But when you imagine the full column, from the first flicker of fading blue down to the edge of the sea floor, the dead center of the ocean begins to look less like a blank and more like a quiet library of lives that have evolved to make the most of darkness, pressure, and time. On the seafloor at Point Nemo, quiet plains, slow creatures, and hidden traces. If you follow the water under Point Nemo all the way down, past the last drifting plankton, past the slow predators and the occasional sinking carcass, eventually you reach the place where the sea ends and the solid earth returns. Here, roughly 3,700 meters beneath the surface, lies an abyssal plain, a broad, gently undulating expanse of sediment that stretches far beyond the reach of any light from above. There are no cliffs looming in the darkness, no jagged reefs, no towering underwater peaks directly beneath the coordinate we call the dead center of the ocean. Instead, there is space and quiet, a floor of fine particles that have taken centuries to fall, and living things that have adapted to a world where change and movement are measured in slow increments. The pressure at this depth is enormous, around 370 atmospheres, each 10 meters adding another layer of force beyond what we experience at the surface. Yet the water does not feel squeezed. It simply is. And the creatures that live here are built in ways that make this kind of pressure ordinary. They have no air-filled lungs or swim bladders that could be crushed. Their bodies are often soft, with minimal internal skeletons or shells. Their chemistry is tuned so that proteins and membranes function reliably under conditions that would destroy shallow water organisms. The temperature, meanwhile, is almost unchanging, hovering near 2 to 4 degrees Celsius year-round. There are no seasons this far down. No winter storms or summer calms. Just a slow, constant cold. The sediment that carpets the seafloor beneath Point Nemo is mostly made of the remains of life from far above. Tiny shells of plankton, fragments of organisms that lived and died in sunlit layers or along distant coasts. Particles of dust and clay carried by air and water from continents many thousands of kilometers away. All of these gradually sink, becoming thinner and smaller as they descend, until they finally come to rest as a soft, fine-grained layer sometimes called marine snow after it has completed its journey. Over geological time, this material can build up into a layer hundreds of meters thick. Each grain is a small piece of history, and together they form a record of changing oceans and climates, stretching back millions of years, compressed into silence. Life here is sparse but present. Benthic worms thread their way through the sediments, feeding on organic matter trapped within the grains. Tiny crustaceans scuttle across the surface, pausing to inspect any fragment that appears richer in carbon than its surroundings. Sea cucumbers, soft-bodied and slow, crawl along like living vacuum cleaners, ingesting sediment and extracting what nutrition they can from it before expelling cleaner particles behind them. Some of these creatures are small, just a few centimeters long, while others can grow to significant sizes. But all of them move with the unhurried motions of animals that do not need to be fast, because nothing down here happens quickly. Occasionally, the seafloor beneath Point Nemo receives a sudden windfall, the remains of a large animal, such as a whale, that has died nearer the surface and sunk intact. When such a carcass arrives, it becomes a temporary oasis of food in an otherwise lean landscape. Hagfish, sleeper sharks, amphipods, and other scavengers converge, guided by the chemical signature of decomposition. In the first phase, the larger scavengers tear as much tissue as they can from the bones. Later, specialized worms and microbes take over, feeding on lipids and proteins trapped within the skeleton. Eventually, even the bones become substrates for microbial films and small invertebrates, until all that is left is a slight elevation in the sediment, soon to be buried by the continuous fall of particles. These events are rare and local, but they form part of the deep sea rhythm beneath even the emptiest looking parts of the map. Alongside natural material, the seafloor under and near Point Nemo has also received some of the most human artifacts possible to hide. Fragments of spacecraft and satellites that have been guided into this remote part of the ocean to minimize risk to people and shipping. By the time those objects reach the bottom, they are usually scorched, broken, and partially eroded by their passage through the atmosphere and water. They rest among the sediments much the way a boulder might rest on a plain, slowly accumulating a thin skin of microbial life and sediment. From the perspective of the deep sea community, they are simply new pieces of hard substrate in a world dominated by soft mud. One day, if they last long enough, they may become completely buried and indistinguishable from the rocks and nodules that form naturally on the abyssal floor. It is tempting to imagine the seafloor beneath Point Nemo as a stage for myths. The resting place of lost cities, the lair of monsters, the focus of unexplained sounds. In reality, the mysteries here are quieter, but perhaps more profound. They concern how life can persist and even adapt in an environment with so little energy input, how chemistry and biology cooperate to recycle every fragment of carbon that drifts down, and how the physical stillness of the plane hides complex interactions happening at microscopic scales. Much of what we know about such places comes from a handful of deep submergence vehicles, remotely operated platforms, and sampling devices that have visited similar abyssal plains elsewhere. Direct observations under Point Nemo itself are scarce, because sending a research vessel to the most remote point in the ocean is expensive and time-consuming, and there is no nearby port to serve as a base. Nevertheless, what we understand about abyssal plains in general gives us a reasonable picture of what lies beneath the dead center of the ocean. There is likely no towering ridge directly under the coordinate, no trench plunging to extreme depths, just a gentle plain of sediment with subtle ripples carved by bottom currents that shift grains over long months and years. Now and then, a deep current may strengthen slightly, redistributing fine material and exposing slightly coarser particles beneath. Small mounds and depressions may mark the burrows of worms or the feeding paths of sea cucumbers. The overall impression, if you could sit there with a light filtered to match the animal's comfort, would be of a very slow landscape, more like a deep, breathing background than an active scene. From the surface, Point Nemo looks like a single point in an empty sea. But when you consider its full depth, from the first faintly lit layers down through the clear twilight, the granular midnight, and finally the sedimented floor, it becomes clear that the dead center of the ocean hides not a void, but a stacked arrangement of quiet systems. Each layer contains its own form of life, its own balance between energy input and survival strategy, its own way of using the few resources that arrive. The abyssal plain at the bottom is the last stage in that vertical story, a resting place for what the ocean has carried and transformed. It does not resemble the busy coasts where waves crash and birds circle, yet it is just as much a part of the sea. In its stillness, it offers a different kind of perspective. That even in the most remote, silent, and pressured depths, the planet is not empty. It is simply moving at a pace that rarely intersects with ours. Listening at the dead center, sound, stillness, and the secrets carried by water. If the seafloor beneath Point Nemo is the quietest plane you can imagine, then the water above it is the quietest concert hall. Out at the dead center of the ocean, far from ports and ordinary shipping noise, the sea becomes one of the best places on Earth not to look, but to listen. Even when the surface seems calm and the abyss below appears motionless, sound is constantly passing through this column of water. It moves more cleanly here than almost anywhere else, because there is so little human activity to drown it out. In a way, the remoteness of Point Nemo is as important to the ear as it is to the eye. And the hidden things in this part of the ocean are often not shapes or colors, but patterns of sound that reveal the slow work of the planet. Sound travels through seawater about 4 times faster than through air, and it loses energy more slowly, especially at low frequencies. The ocean has, built into its physics, a kind of natural wave guide for certain tones. At mid-depths, where temperature and pressure combine just right, there is often a layer known as the SOFAR channel, the sound fixing and ranging channel, where sound waves can become trapped and carried horizontally across huge distances with very little loss of strength. Under wide reaches of the Pacific, including the region around Point Nemo, this channel can sit somewhere between a few hundred and about 1,000 meters deep. A sound entering the channel from above or below tends to be refracted back toward its center, bouncing gently and continuing on rather than escaping upward or downward. It is as if the water column has a quiet corridor where certain pitches can circle the globe. Because of this, the ocean near Point Nemo is one of the places where scientists listen in order to understand what is happening, not just locally, but across vast stretches of sea. Arrays of underwater microphones, called hydrophones, have been used in the South Pacific to pick up the groans of moving icebergs, the distant rumble of underwater earthquakes, the calls of whales migrating thousands of kilometers away, and even the faint signatures of human activity, such as the occasional ship that does venture close. In the 1990s, one of these hydrophones recorded an especially strange low-frequency sound in this part of the world. A rising, drawn-out noise that was later nicknamed the Bloop. For a time, it fired the imagination. Some people speculated about unknown gigantic animals living in the deep. But as more data was gathered and compared, the sound's characteristics, its frequency pattern, its duration, the way it changed over time, matched better with natural ice-related events, such as the cracking or fracturing of large ice masses in the Southern Ocean. What looked like a mystery creature instead became a reminder that in the middle of seemingly empty sea, the ocean still relays the voices of polar ice and shifting plates. The key feature of all these sounds is not that they are loud, but that they are enduring. A blue whale's call, traveling through the Sofar Channel, can be heard hundreds or even thousands of kilometers from where it was made. A low note humming through the dim water. Earthquakes send out seismic waves that couple with the ocean and become long, slow rolls of pressure. Ice shelves collapsing or icebergs scraping along the seafloor produce grinding notes that would never reach the air in the same way. In the water beneath Point Nemo, these signals pass like distant thunder heard through a thick wall. To the animals that live there, they are part of the background environment. To us, when we record and replay them, they are one of the few ways we can sense the wider planet from a single, remote point. Against this large-scale soundscape, the life beneath Point Nemo makes its own, much quieter noises. Many deep-sea fish are nearly silent, but some produce clicks, grunts, or drumming vibrations generated by muscles attached to their swim bladders or by rubbing body parts together. Crustaceans such as shrimp can create tiny snaps that, in shallow coastal waters, add up to a persistent crackling background. In the open ocean gyre, where densities are lower, these biological sounds may not form such a continuous carpet, but they still punctuate the darkness in small bursts. When recording instruments are lowered toward the depths, they sometimes capture brief, irregular blips whose sources are uncertain. A fish adjusting its position, a squid's quick movement, a small rock tumbling down a slope somewhere unseen. The soundscape here is not empty, just sparse and full of pauses. What hides in these pauses is almost as important as the sounds themselves. For most of its depth, the ocean under Point Nemo is free from the persistent mechanical noise that fills busy seas near coasts. The churning of propellers, the thrum of engines, the ping of active sonar used by navies or industries, the clatter of anchors and chains. In those places, human noise can mask or overwhelm natural signals, making it harder for animals like whales to communicate and for scientists to monitor the environment. The central South Pacific is different. Ships pass now and then, but not constantly. There are no harbors nearby, no oil platforms, no industrial fishing fleets working these same coordinates day after day. This makes the region a kind of acoustic refuge, a place where both animals and instruments can hear more clearly. For deep diving whales, such as sperm whales or certain beaked whales that may occasionally traverse this remote part of the Pacific, the clarity of the soundscape can be an advantage. These animals rely heavily on sound for navigation, hunting, and social interaction, using echolocation clicks and complex calls to find one another and to detect prey in darkness. As they dive down into the mesopelagic and deeper zones under and around Point Nemo, the faint noises of distant earthquakes, storms, and ice movements may form a kind of acoustic backdrop. But there is less competition from human-made interference. The dead center of the ocean, from this point of view, is not dead at all. It is simply less cluttered, leaving more space for the original language of the sea. For scientists, the region illustrates how deeply connected the world systems are. A single hydrophone anchored in the mid-depths beneath this remote coordinate can pick up signals from tectonic activity thousands of kilometers away and from icebergs drifting in polar waters. It can hear changes in the frequency of whale song as populations shift their routes with changing climate conditions or as they adjust to altered noise patterns elsewhere in the ocean. It can record the subtle rise or fall in background noise over decades as weather patterns change. Storms become more or less frequent, or as human shipping routes shift in response to economic or environmental developments. From one very empty-looking point on the map, a patient listener can hear the slow music of the whole planet. Down near the seafloor, the soundscape is quieter still, but not perfectly silent. Bottom currents sweeping across the sediment can create faint rustling noises. Occasionally, a small slump of sediment on a nearby slope might send a gentle rumble through the mud. The fall of a large object, such as a whale carcass or a rock broken from a distant ridge, makes a distinctive thud, followed by a long stillness as the soft bottom absorbs the energy. If fragments of spacecraft have indeed come to rest under and around Point Nemo, their final journey would have ended with such a sound, brief and then swallowed. There is no echo chamber down there, no canyon to amplify the impact, just an open, absorbing plain. In this way, what hides in the dead center of the ocean is less a single secret creature or structure and more a pattern. The combined record of thousands of distant events, all carried and softened by water. The remoteness of Point Nemo removes visual distractions and leaves behind a column of sea that functions like a long, clear sensor. At the same time, the deep calm and sparse life within that column show how living things have adapted to use sound without overloading their environment. Every click, every call, every low-frequency hum is spaced out in time and distance, fitting into a soundscape that remains gentle enough to rest in. For a viewer or listener encountering this story in the still of night, the idea that the middle of the ocean is a listening post rather than a void can be a comforting one. Far from shore, beneath a sky that may be bright with stars, the water below is carrying quiet signals between distant parts of the world. The deep under Point Nemo is not broadcasting drama. It is registering the slow movements of Earth's crust, the passage of ice, the migration of whales, the occasional splash of a falling object, and the soft sounds of creatures living in conditions that never hurry them. It is a hidden archive written not in ink or light, but in pressure waves moving through a place where there is almost nothing to get in their way. Invisible rivers, currents, chemistry, and the slow life support of Point Nemo's depths. If you could drain the water away from the region beneath Point Nemo, what you would see first is not a single massive hole in the planet, but a shallow, slow basin in the great circulation of the world's oceans. The South Pacific Gyre, which cradles Point Nemo, is part of a vast, invisible river system that moves not on the surface like a visible stream, but through layers of water, guided by differences in temperature and salt. That circulation touches the deep under Point Nemo, just as surely as winds touch the surface, and it is this movement, more than anything else, that keeps the water column alive, even where the sea seems most isolated. The upper few hundred meters around Point Nemo belong to a broad band of relatively warm, well-mixed water that is pushed around the South Pacific in a slow, clockwise loop by the combined effect of winds and Earth's rotation. Because this gyre is far from coasts and major upwelling zones, it lacks the nutrient injections that feed plankton blooms elsewhere. Sunlight falls, but the water has little to grow in response. So the surface remains comparatively clear, like a glass lid over the ocean's deeper workings. When plankton do grow and die, their remains begin a long, calmly vertical journey. They become part of the marine snow that sinks through the column, feeding life at depths where no sunlight reaches directly. Below this surface band lies a transition where temperature falls and density rises, forming what oceanographers call the thermocline. Around Point Nemo, this transition can be particularly sharp. Warm water above, colder water below, a kind of soft boundary that many animals cross with ease. but that still help structure where nutrients and oxygen are slowly distributed. Far beneath that, filling most of the deep column, lies water that originated in distant, cold places. Some of it sank near Antarctica, where frigid, salty water becomes heavier than the water around it and plunges down slopes into the abyss. Some originated in the North Atlantic. Over years and decades, these deep waters flow along the bottom of basins and across entire oceans, eventually passing under even the most remote points. By the time these deep water masses reach the region beneath Point Nemo, they have not seen the surface in a very long time. They carry with them a memory of the last atmosphere they touched. The temperature, carbon dioxide content, and oxygen they absorbed before they sank. As they move, they gradually gain carbon from decaying organic matter and lose oxygen to the respiration of deep living organisms. The deep sea under Point Nemo is thus part of a global conveyor, not an isolated pool. When we say that this place is the center of the ocean, we do not mean that it is cut off. Its remoteness is real in terms of distance to land, but chemically and physically, it is part of long, slow loops that tie the whole planet together. The creatures living in these waters are tuned to those loops with a precision that feels almost like trust. Many deep-sea animals rely on the constancy of temperature and the steady, even if minimal, flow of oxygen. Metabolisms are set low. Growth is gradual. Reproduction is spaced out over years. A sudden, large change in conditions would be far more disruptive here than it might be in a fast-moving coastal environment. But such changes are rare. Instead, what the inhabitants of the deep under Point Nemo experience is a quiet, gradual evolution of background conditions. A fraction more carbon in the water, a fraction less oxygen, slight shifts in pH. These changes matter, but they arrive with the slowness of drifting continents rather than the speed of a surface storm. Chemically, the water beneath Point Nemo holds traces of almost everything that has happened at the surface above it, and in far-off regions it is never seen. Tiny amounts of pollutants, such as microplastics and industrial compounds, can eventually find their way even into these depths, carried by currents and sinking particles. The South Pacific Gyre is known at the surface as an accumulation zone for floating debris, although its litter density is lower than in some other gyres. Over time, pieces that break down and sink can become part of the deep landscape. Even here, far from major sources, human fingerprints exist. But they are faint compared to the vastness of the basin, and most of the chemistry is still dominated by natural processes. Respiration, bacterial breakdown, mineral reactions with sediments, and the long-term burial of carbon in the seafloor. Within this watery framework, life under Point Nemo follows simple lines of energy. Primary production, the first capture of solar energy into food, happens mostly far away and above. By the time that energy reaches this depth, it has been converted, eaten, excreted, recycled, and repackaged many times. Bacteria and archaea play a central role. They coat particles, colonize tiny aggregates of organic matter, and form films on any stable surface, from small stones to fragments of sinking shells. They turn complex molecules into simpler ones, releasing nutrients back into the water that can be reused even in darkness. In some parts of the deep ocean, hydrothermal vents and seeps provide chemical energy directly from Earth's interior, supporting chemosynthetic communities that do not rely on sunlight at all. Under Point Nemo, where no major vent fields are known, the deep sea leans more heavily on what falls from above. Currents passing through this region do not roar. They creep, carrying entire water masses at the speed of a slow walk or less. Over years, they may shift slightly in position, rise or sink a little as global patterns change. The creatures in these waters probably do not sense the currents as rivers the way surface sailors do. For a deep sea fish or a drifting jelly, the water around them simply is, and its movement becomes the background for their own smaller motions. Yet those currents decide, over decades, how much oxygen will reach a particular depth, how quickly a patch of water will be refreshed, how long a piece of carbon will remain in circulation before it is buried. In that sense, the bodies of animals under Point Nemo are made not only from local resources, but from a mosaic of histories carried to them from all over the globe. For us, thinking about this can turn the dead center of the ocean into a calming paradox. At one level, it is the most remote coordinate we can name, a dot surrounded by thousands of kilometers of sea. At another level, it is a crossroad in a system that connects poles, coasts, and basins into a continuous whole. What hides beneath Point Nemo is not a separate world, but a profound example of connection happening too slowly and too quietly for casual observation. The deep currents, the subtle chemical gradients, the steady rain of particles, the low and patient metabolisms of deep life all work together without spectacle, keeping a faraway part of the sea in balance. Listening to that idea and imagining those invisible rivers flowing under an empty horizon can itself feel like sinking into a deeper kind of stillness. Unknown residents, what we haven't seen yet, in the center of the ocean. When we ask, what hides in the dead center of the ocean? The most honest answer is not a specific creature or structure, but a simple admission, more than we have yet managed to see. The area beneath Point Nemo has not been explored with the same intensity as waters closer to busy coasts or famous trenches. Research ships tend to sail where ports are near and logistics are easier. Remotely operated vehicles and crewed submersibles are expensive to deploy, and their dives are usually planned where scientists expect a high return of data. Over active vents, steep slopes, coral reefs, or known fishing grounds. Point Nemo sits far from all these. It is not entirely untouched, but it is undersampled. In that undersampling lies a quiet kind of mystery that is less about monsters and more about the limits of our attention. Based on what we know from similar depths in other parts of the open Pacific, the community beneath Point Nemo is likely to include many groups we recognize: lanternfish, bristlemouths, dragonfish, small deep-sea sharks, squid of various sizes, gelatinous zooplankton, crustaceans, worms, sea cucumbers, brittle stars, and countless microbes and viruses. These form a fairly consistent cast across much of the world's abyssal plains and midwaters. Within that cast, however, there is plenty of room for unrecorded variations, species that have never been collected, color patterns, or bioluminescent arrangements that have never been photographed, behaviors that have never been observed directly. Each basin, each gyre, each combination of depth, temperature, and chemistry offers slightly different niches, and life has had millions of years to experiment quietly with how to fill them. When a new expedition does lower cameras into such regions, it is common to find unfamiliar forms alongside known ones. Sometimes these differences are subtle. An extra row of photophores on a lanternfish, a slightly altered jaw shape in a dragonfish, a jelly with a unique arrangement of tentacles. At other times, they are more striking. A siphonophore far longer than the ones cataloged before, or a ketanophore that refracts light in a pattern no one has seen. Under Point Nemo, such surprises almost certainly exist, simply because effort has been limited. The ocean has not been required to show its workings here. It continues them, whether or not we look. Beyond animals large enough to be seen with cameras, there is another layer of hidden diversity, the microscopic life that pervades the water and the sediment. Bacteria, archaea, and viruses are present in staggering numbers, even in the deep sea. Many of them specialize in breaking down particular kinds of organic matter or in using chemical gradients that are too weak to power larger bodies but sufficient for single cells. Modern techniques such as environmental DNA sampling have begun to reveal just how many lineages exist in a scoop of seawater or mud. In regions that have been sampled, new branches of the tree of life are regularly discovered. Groups that represent entire evolutionary experiments in metabolism and structure, previously unknown simply because no one had looked in that exact place with the right tools. Given the remoteness of Point Nemo, it is reasonable to imagine its depths as home to a set of microbial stories that we have not yet read. This sense of quiet unknowns extends even to simple measurements. How often does a whale carcass fall to the seafloor under Point Nemo compared to other regions? How thick is the sediment in the exact area? How does the local community change between, say, 3,000 and 4,000 meters? What proportion of the marine snow reaching this abyss originates from nearby versus distant parts of the Pacific? These are not questions that hold drama in a conventional sense, but they are the kind of puzzles that occupy oceanographers when they think about the deep sea as a whole system. The answers would help refine our understanding of how carbon is stored, how nutrients are recycled, how robust deep communities are to change. At present, for Point Nemo, many of those answers are estimates based on broader patterns, not direct observations. There is also a human dimension to what remains hidden. For many people, the phrase, "dead center of the ocean," conjures images borrowed from fiction. Sunken cities, ancient machines, colossal, unseen animals. Authors like Jules Verne and H.P. Lovecraft placed secrets in remote seas because remoteness itself feels like an invitation to imagine. The coincidence that Lovecraft's fictional city of R'lyeh happens to be near the real-world coordinates of Point Nemo only reinforces that tendency in some minds. Yet as instruments have advanced and data sets expanded, what we find beneath the waves is both more ordinary and more profound than those older fears suggest. The deep sea is not empty, but its richness lies in its persistence and its adaptability, not in singular terrors. The things that truly hide there are the daily lives of animals that rarely need to hurry, the long-term adjustments of microbial communities to shifting conditions, and the gradual burial of carbon that helps keep the climate at the surface stable enough for us not to notice how much work the ocean is doing. For a calm documentary, this quieter answer is a gift. It allows the story of Point Nemo to stay grounded in truth while still holding space for wonder. You can say, honestly, that there are likely species beneath this point that have never been recorded, behaviors that have never been witnessed, and interactions that happen entirely beyond the reach of our current monitoring. You can also say, just as honestly, that the deep under Point Nemo is probably not radically different in its overall structure from other abyssal and midwater regions of the South Pacific. It is an example of a pattern, not an exception to it. The mystery here is not that the center of the ocean breaks the rules, but that it follows them so reliably, even when we are not paying attention. Imagining this can be quietly comforting. Far below the waves, in a column of water and on a plain of sediment that few people will ever see, life goes on in forms that are both familiar and unknown. Lanternfish rise and fall, jellies drift, worms weave through the mud, microbes work continuously on particles that have fallen for months. No one there knows where Point Nemo sits on a map. The ocean does not recognize our names for its coordinates. It simply continues, and in doing so, hides nothing malicious at the dead center, only processes that are too slow and too deep for us to notice in our everyday lives. What remains hidden, for now, is mostly our own detailed understanding. And as long as that is the case, the middle of the ocean will remain a place where the imagination can rest gently on a foundation of calm, patient reality. Deep time under a single point. How long the center of the ocean has been quietly working. When we imagine Point Nemo on a map, it is a modern idea. Calculated on computers, named in the late 20th century, shared online and in documentaries. But the reality under that name has been part of Earth's story for longer than any continent's current shape. The waters under the dead center of the ocean have been circulating, cooling, mixing, and supporting life for millions of years, long before our species appeared to give coordinates and titles to it. Thinking about Point Nemo in terms of time stretches the image from a simple dot in the present to a long vertical thread through history. The seafloor beneath Point Nemo, that broad abyssal plain of fine sediments, is layered like a book that has been written in dust and shells instead of ink. Each millimeter of mud may represent hundreds or thousands of years of slow accumulation. Tiny skeletons of plankton that bloomed and died in ancient seas have been raining down and settling there, one after another, through warm ages and ice ages, through shifts in the positions of continents and changes in the tilt of Earth's axis. Chemical analyses of such sediments in other parts of the ocean have revealed repeating patterns linked to orbital cycles, volcanic events, and long-term climate swings. Although we have not taken as many cores from the precise seafloor under Point Nemo as from more accessible regions, the same processes are at work. The quiet there is not the quiet of nothing happening. It is the quiet of something happening so slowly that a human life can barely register it. The deep water masses that flow past that plain also tell a story measured in centuries. When a parcel of cold, salty water sinks in the North Atlantic or near Antarctica, it takes on a distinct fingerprint of temperature and dissolved gases. It then begins a long journey along the bottom of basins and up slopes, mixing only gradually with surrounding waters. It may take hundreds of years for such a parcel to pass from the high latitudes where it formed to the central South Pacific. By the time it moves under Point Nemo, the atmosphere it last touched belongs to an earlier era. In this way, the deep sea acts as a memory bank for the climate, storing not only carbon and heat, but also the record of atmospheric conditions long past. Life in the deep under Point Nemo moves on a similarly extended timeline. Many abyssal animals are thought to grow slowly, reaching maturity over decades. Some deep-sea corals in other regions have been dated at hundreds or even thousands of years old. Their skeletons preserve chemical traces of the waters that flowed around them as they grew. While those specific long-lived animals may be less common on a soft sediment plain than on rocky outcrops, the principle holds. In the deep ocean, individual lifespans and population changes are often stretched out over periods that match or exceed human generations. A single worm burrow might be inhabited, abandoned, and reoccupied many times over decades. A population of small fish might wax and wane in response to subtle shifts in food supply over centuries, without anyone at the surface ever noticing a difference in the waves above. From the perspective of deep time, Point Nemo's status as the most remote point from land is a fleeting label. Continental configurations have changed before and will change again. Millions of years ago, when the supercontinent Pangaea was intact, there was no South Pacific gyre in its current form and no middle of the ocean in quite the same place. Millions of years from now, if tectonic plates continue to move, the outlines of the continents and basins will shift. Currents will follow new paths, and a different coordinate might claim the title of oceanic pole of inaccessibility. The present-day Point Nemo is a snapshot in a long film, and the life beneath it is adapted more to the steady undercurrent of planetary physics than to the brief moment in which humans have noticed and named it. Yet our short lives do intersect with these long processes in subtle ways. The carbon that human activities have added to the atmosphere over the last 2 centuries is gradually being absorbed by the ocean. Some of it stays near the surface, some sinks with particles to the deep, and some enters the very water masses that will one day pass beneath Point Nemo. A molecule of carbon dioxide released in a city may eventually dissolve into seawater, get taken up by a plankton cell, sink as part of marine snow, and become part of the deep sea sediments far from any shore. That journey can take years to decades for the first steps, and thousands of years for the last. The deep under Point Nemo is one of the vaults where such carbon can end up stored for very long periods, helping to buffer climate changes at the surface. In this way, even a remote point is involved in the slow balancing act that keeps conditions at Earth's surface within the ranges we consider habitable. For someone listening to this story at night, it can be calming to think of the dead center of the ocean as a place where time stretches and softens. The waves on the surface may change from day to day, but most of what is happening below them unfolds on scales so extended that no single storm, no single human year can disturb them. The sediments continue to accumulate grain by tiny grain. The deep currents continue to flow at their own pace, carrying memories of old climates. The animals continue to live, feed, reproduce, and die according to rhythms that are largely unaware of our presence. The coordinates we have assigned and the stories we tell are brief visitors to a system that has been working quietly for longer than any map has existed. Thinking about Point Nemo this way shifts the question: what hides in the dead center of the ocean? From the search for a hidden object to an awareness of hidden duration. What is concealed there is not a singular secret, but the continuity of processes that we rarely have the patience to feel. The center of the ocean is a place where Earth's long, deep breath is stored, steady enough that we can let our own breathing slow to match it for a while. A night at Point Nemo, sky above, depth below, and the feeling of being in the middle. To complete the picture of Point Nemo, it helps to return gently to the surface for a moment, because what happens above and what happens below are more connected than they appear. Imagine a calm night floating at the dead center of the ocean. There is no coastline glow in any direction, no nearby ship lights, only the faint trace of distant stars spread across the sky. The horizon is a nearly perfect circle. Waves rise and fall softly, shaped by winds that have crossed thousands of kilometers with nothing to interrupt them. In that setting, the word middle begins to feel different. It is not the middle of a crowd, but the middle of space. Above you, the sky over Point Nemo can be among the darkest on Earth when clouds are absent. With no cities or towns nearby, there is almost no artificial light to wash out the stars. The Milky Way, in the right conditions, would appear as a pale band stretching from one side of the horizon to the other. Planets would shine more steadily than they do above land, cluttered with light. Occasionally, a satellite might drift across, a slow moving point reflecting the sun's rays long after local sunset. High above, spacecraft in low Earth orbit move over this region along their own predictable paths. From their vantage point, Point Nemo appears as a patch of uninterrupted blue by day and black by night. Devoid of land edges, a kind of visual rest area on the planet. Below you, at the same moment, the water is busy in its own unhurried way. Lanternfish are rising through the twilight zone to feed closer to the surface. Jellies are drifting upward with tentacles extended, intercepting small plankton carried by gentle currents. Deeper down, dragonfish and squid are adjusting their depth in response to changes in light and the movement of prey. On the seafloor, worms and sea cucumbers are continuing their patient work of sifting and recycling sediment. None of these creatures have any sense that they are under a famous coordinate. They respond only to the cues available: light fading or brightening, water temperature shifting slightly, the arrival of food particles, faint vibrations, or chemical traces. In between the sky and the seafloor, the full column of water is quietly conducting heat, sound, and chemicals. If a distant earthquake occurs on a mid-ocean ridge thousands of kilometers away, its tremors may eventually be felt as long, low-frequency motions in the water column, picked up by sensitive instruments, but barely perceptible otherwise. If a storm blows up at the surface a day's journey away, its waves may propagate outward as long swells, eventually passing under your imagined position without forceful braking. If a whale passes through the broader region, its calls may travel through the SOFAR channel, a faint murmur in the deeper layers. All of this is happening in one continuous volume of water, with your small point on the surface and the abyssal plain beneath it functioning as temporary reference markers in a system that would keep working without them. There is a particular kind of calm in realizing how indifferent this environment is to our presence. Not hostile, just indifferent. The ocean at Point Nemo does not lean toward or away from us. Its processes do not speed up when we pay attention or slow down when we forget. The carbon cycle, the heat exchange, the slow burial of sediments, the gentle drift of animals all proceed according to physics and biology that were set in motion long before we arrived. For a viewer or listener seeking rest, this realization can be reassuring. The world has layers that continue to function even when we are asleep, and some of the most important of those layers are far from the noise and urgency of human activity. In that imagined night at Point Nemo, you could look up at the stars and know that above them, spacecraft have used the ocean's remoteness as a safe place to fall. You could look down into the dark water and know that somewhere below, fragments of those machines rest on the sediment, slowly becoming part of the landscape. At the same time, uncounted tiny organisms are building their own structures: shells, skeletons, protective cases from the minerals dissolved in the seawater, only to have those structures eventually return to the sediment in their turn. The scene is one of continuous cycle, not of stasis, and yet it feels still because so much of it happens at scales beyond everyday perception. From a storytelling perspective, this is where the idea of what hides in the dead center of the ocean is resolved not with a single revelation, but with a layered understanding. What hides there is a connecting volume between sky and seafloor, between different parts of the globe, between short human moments and deep planetary time. It is a place where you can feel, in imagination, equally far from all coasts, and yet entirely within the fabric of Earth's systems. There is nothing lurking there in the sense of awaiting danger. There is instead an ongoing, gentle interplay of light and dark, motion and rest, sound and quiet, life and decay, all repeating in patterns that do not depend on being watched. Lying back, either in reality or in thought, and picturing that scene, the star-filled sky, the empty horizon, the full depth below, can feel like allowing yourself to float in a space that is both anonymous and deeply connected. In that sense, Point Nemo is not only a geographic curiosity, it is a kind of mental place, a symbol of how small we are and how continuous the world is. Knowing that, you can let the image sit and slowly fade, like waves losing their shape as they spread, while the center of the ocean continues to be exactly what it has been for a very long time: quiet, patient, and complete without needing to be seen. How we study a place we almost never see, quiet science at the world's middle. For all the detail we can imagine about the waters beneath Point Nemo, very little of it comes from direct, repeated visits to that exact coordinate. Instead, most of what we know is stitched together from a mix of global patterns, a handful of measurements, and the quiet reach of instruments that can listen, drift, or sink where ships and people rarely go. The dead center of the ocean is not easy to work in. There are no nearby ports from which to launch expeditions, no coastal bases with warehouses and workshops, no quick resupply if something breaks. Getting there at all requires days of sailing across open water. Once there, a research vessel is essentially alone. Yet, piece by piece, science has found ways to learn about even such a remote part of the sea. The most basic tools are those that simply measure the properties of the water itself. Oceanographers often use devices called CTD rosettes, frames carrying bottles and sensors that can be lowered from the ship all the way down to the seafloor and brought back up again. CTD stands for conductivity, temperature, and depth. Key parameters that, together with salinity and oxygen, describe how water masses are structured and where they came from. When a CTD profile is taken near Point Nemo, it reveals a familiar pattern. Warm, less dense water in the upper layers, a marked thermocline where temperature drops quickly, and then colder, denser deep water that has flowed in from high latitudes. Each depth holds its own fingerprint of dissolved gases and nutrients, showing, among other things, how much oxygen has been used up by the slow respiration of deep sea life. To capture movement, scientists release instruments that do not stay attached to the ship at all. Drifting floats, like those used in the global Argo program, are small autonomous devices that sink to a set depth, drift with the currents for days or weeks, then rise, measure profiles on their way up, transmit the data by satellite, and sink again. Over time, a network of these floats builds a picture of how water masses are moving and changing, even in remote regions. Some deep floats are designed to go well below the usual 1,000 or 2,000 meters, sending back glimpses of conditions in the abyss. Even if only a few floats pass through the area under and around Point Nemo, their combined records help trace the invisible rivers that we imagine curling through the basin. For the seafloor, different tools are needed. Ships can map the shape of the bottom using multi-beam sonar, which sends sound pulses down and records the echoes as they bounce off the seabed. The travel time and strength of the returning sound tell us about depth and roughness. This technique has shown that much of the seafloor beneath the central South Pacific is relatively flat, abyssal plain, punctuated here and there by seamounts and small hills, but without dramatic trenches directly under our named point. The resolution is not perfect. Details smaller than a few hundred meters across can be missed, and coverage is incomplete. But over decades, more and more swaths of ocean have been mapped in this way, slowly sharpening our picture of the world's least visited floors. To examine the life there, scientists sometimes send down traps, nets, and cameras. Free-falling landers are simple frames equipped with lights, cameras, and bait. They are released from the ship to fall unpowered to the bottom. Once there, they record whatever comes to investigate the bait. Fish, crabs, amphipods, sometimes curious deep-sea sharks. After a preset time, a release mechanism drops a heavy weight, and the lander floats back to the surface for recovery. Such tools have been used in many parts of the deep ocean, including remote gyre regions, revealing that even apparently barren plains can attract a diversity of scavengers when food is available. Although not every region under Point Nemo has been directly sampled in this way, similar depths nearby give us a strong indication of what to expect. In the midwaters, sampling is trickier. Nets can be towed at different depths, their mesh size chosen to catch animals of particular sizes, but the deep scattering layer is delicate. Many gelatinous creatures burst or dissolve when netted, leaving only fragments. To get better, more natural views, Researchers use towed or free-swimming camera systems, some equipped with red lights that are less visible to many deep-sea animals. Slowly, these eyes in the dark have begun to show lanternfish schooling in loose bands, jellies pulsing gently, and predators hovering with lures glowing. Most of these observations come from better studied regions. But again, because the mid-ocean gyres share broad characteristics, it is likely that the waters beneath Point Nemo host similar communities. Another powerful method for learning about a place we rarely visit is the analysis of environmental DNA, or eDNA. All living things shed genetic material into their surroundings: skin cells, scales, mucus, excretions. By filtering seawater and extracting DNA from it, scientists can identify traces of organisms that passed through recently, even if those organisms were never seen or captured. This approach is still developing, but it has already revealed hidden diversity in coastal and open ocean waters. A sample from near the surface or at depth under Point Nemo could, in principle, tell us which fish, jellies, crustaceans, and microbes inhabit the column, even without a single animal being brought aboard. Taken together, these tools form a quiet observational network. None of them need constant human presence in the way a coastal lab does. Floats drift unattended. Hydrophones listen and store sound. Landers fall and rise on their own timers. Satellites overhead track sea surface height, temperature, and color, giving hints about currents and productivity even where no ship is currently sailing. The remoteness of Point Nemo makes hands-on work more difficult, but it also makes the area an ideal test of how far careful instrumentation and global modeling can go in describing a place indirectly. From a calm storytelling angle, this reminds us that we live in a time when we can understand, at least in outline, something about even the furthest corners of our planet without physically occupying them. Point Nemo is both proof of our absence and evidence of our reach. Beneath it, the deep sea continues to operate on its own terms, but thin threads of data connect that operation to screens and notebooks on distant shores. Those threads are not loud, but they are enough to turn the unknown of the center of the ocean into a gentle, unfolding, not yet fully known. Point Nemo in a changing ocean, subtle shifts in a quiet place. The dead center of the ocean feels timeless when we imagine it. The same swells, the same stars, the same deep currents rolling by beneath, year after year. In many ways, that impression is accurate. The deep sea changes slowly. Temperatures are stable to within a degree or two. The seafloor accumulates sediments at a leisurely pace. Animals live and die without sudden swings in their environment. Yet even here, far from coasts and storms and cities, the ocean is not completely insulated from change. The broader shifts affecting Earth's climate and chemistry eventually reach this remote basin as well, though they do so in ways that are gentle to observe but significant over time. At the surface, the waters around Point Nemo are part of the global pattern of warming. Sea surface temperatures in many regions of the world have been creeping upward over recent decades, and the Central South Pacific is no exception. A small increase of a degree or so might not seem like much compared to the daily range on land. But for marine ecosystems, even modest warming can alter stratification, currents, and the timing of plankton blooms. A slightly warmer surface can strengthen the layering between warm upper water and cold deep water, making it harder for nutrients from below to reach the lighted zone. In an area that already has low productivity, this could mean that surface life becomes even sparser, with knock-on effects for the amount of organic material that sinks to the depths. Carbon dioxide absorbed from the atmosphere also affects these waters. As CO2 levels rise in the air, more of it dissolves into the ocean, forming carbonic acid and gradually lowering pH, a process known as ocean acidification. This change is most pronounced near the surface, where exchange with the atmosphere is direct. Over time, some of the altered water subducts and joins deeper currents, carrying the chemical shift downward. In the central South Pacific, this means that, slowly, the waters passing under Point Nemo will become slightly more acidic than they were centuries ago. For many deep-sea organisms, especially those that build shells or skeletons from calcium carbonate, even small changes in acidity can influence how easily those structures form and dissolve. Oxygen levels are also part of this subtle story. Warmer water holds less dissolved oxygen than cooler water, and stronger stratification can limit the ventilation of deeper layers. In some parts of the world, this has contributed to expanding oxygen minimum zones, regions at mid-depth where oxygen concentrations are very low. The South Pacific already has one of the larger oxygen poor zones at intermediate depths, though the exact boundaries and intensities vary. The waters under and around Point Nemo may experience small shifts in where these layers sit and how intense they are. For animals adapted to a narrow band of oxygen availability, such shifts can change where they are comfortable living, even if the shifts happen gradually. On the seafloor, the arrival of extra carbon from human activities is more muted but still present. Increased primary production in some areas, altered by nutrient runoff or changes in circulation, can send different patterns of marine snow into the deep. At the same time, if surface productivity declines around Point Nemo because of stronger stratification, the sediments beneath might receive slightly less new organic material over time. The balance between what is falling and what is being respired could adjust, influencing the structure of the benthic community. Which species of worms, crustaceans, and microbes dominate? How densely they are packed? How quickly they process the material they receive? Plastic and other pollutants, tiny at the scale of the basin, but large compared to the historical baseline, also drift into even these remote reaches. Floating debris can enter the South Pacific gyre and become trapped in its slow spin, breaking down into smaller fragments that eventually sink. Microplastics have been found in deep-sea sediments and in the bodies of animals from trenches and plains far from land. While the densities are low compared to coastal hotspots, their presence marks a subtle change. The deep center of the ocean carries, in microscopic form, evidence of activities that mostly take place on land and in busy shallow seas. The animals and microbes interacting with these particles may be doing so in ways we do not yet fully understand. Despite all of this, the pace of change at depth below Point Nemo remains slow compared to surface experiences. A single human lifetime might span only the early stages of a shift that will take centuries to fully unfold. This does not make the shifts unimportant, but it does mean that, from the perspective of someone listening now, the deep still feels largely as it has for a long time. Dark, cold, quietly inhabited, and only gently aware of the adjustments taking place in its chemistry and physics. In a calm narrative, this can be framed not as impending catastrophe in the middle of nowhere, but as an invitation to think about connection responsibly. The fact that gases we release in cities can, over decades, alter the properties of water under the most remote point in the ocean is both humbling and sobering. It underscores how continuous the planet is. At the same time, the persistence of deep patterns, the continued operation of the biological carbon pump, the constancy of abyssal temperatures, the endurance of deep sea communities, shows that the ocean retains a huge capacity to buffer, adapt, and maintain function, even as it absorbs change. So, when we ask, what hides in the dead center of the ocean? One of the answers is this: a slow record of our time. In the temperature profiles, in the carbon content of waters, in the pH and oxygen levels, in the composition of sediments and the microplastics embedded within them. Future scientists will be able to read the signature of the era when we learned what Point Nemo is and began to tell stories about it. Those signatures will be layered on top of older ones left by ice ages, volcanic eruptions, and natural climate swings. Under that coordinate, as under many others, the sea will continue to write history in gradients and grains, gently, even when we are not looking. For now, for someone trying to rest while thinking about this place, the main feeling to take away is one of scale and softness. The center of the ocean is vast, connected, and slowly changing, but not in a way that demands alarm in this moment. Its processes are long and patient. They will continue to unfold whether we observe them or not. And knowing that can make the thought of Point Nemo feel less like a source of fear and more like a reminder that the world has depths of quiet endurance underneath our brief days. Myths, stories, and the gentle truth of the ocean's center. For a place defined by distance and quiet, Point Nemo has collected a surprising amount of story. Long before anyone calculated an official oceanic pole of inaccessibility, remote waters in the South Pacific existed in imagination as much as in charts. Sailors spoke of endless horizons, of weeks without sight of land, of seas so empty that it felt as if the world had narrowed to nothing but sky and water. When modern mapping and satellite navigation removed much of the uncertainty from ocean travel, that old narrative of mystery did not disappear. It simply moved slightly, settling into coordinates and names like Point Nemo, which became symbols of the last blank feeling left on the map. Fiction loves such symbols. Jules Verne placed Captain Nemo and his submarine, the Nautilus, in remote, largely unseen corners of the world's oceans, where he could move without being easily found. H.P. Lovecraft, many decades later, located his fictional sunken city of Arlaia in a distant South Pacific region, giving it coordinates that modern readers later noticed were close to what would be called Point Nemo. These stories do not describe real geography, but they borrow its flavor. The idea that something could lie hidden in a place so far from any shore taps into a simple intuition. If no one goes there, anything might be there. As instruments and observations improved, it became clear that the central South Pacific does not host sprawling lost cities or improbable beasts larger than ships. What it does host is a quieter kind of strangeness that is no less real for being subtle. Animals with transparent bodies and light-emitting organs, fish with telescopic eyes and oversized jaws, jellies that pulse slowly in waters so dark that even their faint glows feel bright. Microbial communities that thrive on concentrations of nutrients too low to support larger life. The truth, in other words, is stranger in detail, but calmer in mood than the monsters of older tales. The bloop sound recorded in the late 1990s is a good example of how story and reality intersect around Point Nemo. When that low, powerful noise was first heard on hydrophones in the southeastern Pacific, roughly in the same quadrant of the ocean, it sparked speculation. Its frequency pattern was superficially similar to some biological sounds, and people quickly imagined giant, unknown animals making calls in the deep. As more data were gathered, however, researchers found that the sound's characteristics matched those produced by icebergs cracking and breaking apart, or by ice interacting with seafloor and other ice. The bloop turned out to be part of the voice of ice, not a creature. In the end, this explanation did not erase the wonder. It simply redirected it. The idea that vast pieces of ice, far from sight, can make noises that carry through entire ocean basins is its own kind of awe. The spacecraft cemetery narrative adds another layer. Knowing that fragments of human-made machines, from small satellites to large station modules, have ended their journeys in the waters near Point Nemo gives the place a role in our technological story. Here, where traffic is otherwise scarce, objects from orbit have met the sea, burned and broken by their descent. They now rest on the abyssal plain alongside ancient shells and slow-growing nodules. Fiction might be tempted to imagine them as a hidden scrapyard filled with intact relics. Reality paints a quieter picture. Pieces scattered over a vast area, corroding slowly, buried gradually in sediment, becoming just another texture on the seafloor. The myths, once examined, turn out not to live in the water itself, but in us. We create them to fill gaps where we do not yet have detail, or where the scale of a place makes it difficult to hold in everyday thought. What hides in the dead center of the ocean, in that sense, is partly our own tendency to project narratives onto distance. As we learn more, those narratives can be adjusted without needing to be abandoned entirely. The sea remains a powerful backdrop for reflection and story, but now those stories can be anchored in the gentle, steady behavior of real systems. In a calm documentary, it is possible to respect both the stories and the science. One can acknowledge the literary associations, the imagined cities, the speculative creatures, and then set them gently alongside what we know. The slowly circulating currents, the deep scattering layers of migrating fish, the abyssal plains of soft sediment, the occasional whale fall, the gradual chemical changes spreading through the basin. The contrast between the dramatic myths and the understated reality highlights something important. The ocean does not need exaggeration to be impressive. Its true rhythms are vast enough. For someone listening in the quiet of night, this realization can be relieving. There is no lurking horror in the middle of the sea, waiting at a particular coordinate. There are only the accumulated results of physics and biology working together over long timescales. That includes glowing fish and jellies, yes, and steep environmental gradients and immense distances with no land in sight. It includes our own hardware resting on the bottom and sounds from ice and earthquakes traveling through the water. But none of these elements are out to surprise us. They simply exist. Understanding this does not erase the sense of mystery. Instead, it transforms it into something gentler. The unknown in the center of the ocean is not a threat. It is a set of questions we have not finished asking. What exact species live at a given depth under Point Nemo? How are they related to those in nearby basins? How do their populations respond to long-term changes in food supply and chemistry? These questions are open not because the ocean is deliberately hiding the answers, but because our time, resources, and attention have been limited. The sea is patient. It will be there whenever we are ready to look more closely. In this light, the stories that once imagined dangers can be reinterpreted as invitations. They remind us that there are still parts of the world we do not know well, even with satellites overhead and global positioning systems in our pockets. Point Nemo, as a symbol, becomes not a place of dread, but a place where we can let our sense of curiosity rest without urgency, knowing that the truth beneath that point is intricate, consistent, and quietly ongoing. What hides in the dead center? A gentle answer. By now, the phrase dead center of the ocean may feel different than it did at the beginning. At first hearing, it can sound cold, sharp, and lonely, like the eye of a storm or the middle of an empty room. But after spending time with Point Nemo in imagination, moving from the surface horizon to the twilight layers, the midnight depths, the abyssal plain, the soundscape, the currents, the slow changes, and the unseen residents, the phrase softens. The center is still there, a coordinate surrounded by thousands of kilometers of water. But what hides beneath it no longer feels like an ominous secret. It feels more like a layered, steady presence. At the surface, what hides is simply distance. From Point Nemo, no land is visible in any direction. That absence of shorelines is unusual in our daily experience, and it draws attention. Yet it is also straightforward. It means that ships are rare, harbors absent, and artificial light minimal. It allows the sky to be dark and full of stars, the horizon to be a clean circle, and the wind and waves to be shaped by very large scales. The empty look of this spot on a map is largely a human perspective. The ocean itself does not plot its own remoteness. In the midwaters, what hides is motion that does not show at the surface. Lanternfish and other small fishes rise and fall each day in numbers so vast that, collectively, they reflect sonar like a false seafloor. Jellies and other gelatinous animals drift in clear water that looks empty from above, yet is full of delicate bodies. Predators lie in wait with slow patience, using bioluminescent lures and sensitive noses instead of speed and vision. The water conducts sound across basins, carrying the calls of whales, the grind of ice, and the distant thump of earthquakes through layers where there is no light at all. All this activity happens without breaking the surface into obvious signs. At the bottom, what hides is a plain that feels almost like another kind of sky. A broad, dim, and gently textured field of sediment where worms, sea cucumbers, and small crustaceans move quietly. Now and then, a whale carcass arrives, creating a brief, intense feast followed by a return to leaner conditions. Fragments of human-made objects rest here too, spaced far apart across the sediment, slowly being weathered and covered. The scene is not dramatic in the usual sense. It is slow, persistent, and balanced on the knife edge between scarcity and sufficiency. Through all of these layers, what hides most consistently is time. The processes that define the deep under Point Nemo are slow enough that a human life touches only a small portion of their cycles. Deep currents that pass under that point carry memories of climates long past. Sediments accumulate too gradually for a person on deck to notice any change year to year. Deep sea animals grow, reproduce, and die on schedules that do not align neatly with our calendars. Even the signatures of modern changes, slight warming, altered chemistry, traces of pollutants, are spreading into this region at a pace that makes them easy to miss moment by moment, even as they accumulate significance in the long run. So when we ask, what hides in the dead center of the ocean? A gentle answer might be this: nothing singular, everything continuous. There is no single creature waiting, no sudden revelation at a specific depth. Instead, there is the ongoing work of Earth's systems, concentrated in a place where our presence is almost entirely conceptual. The center of the ocean hides the fact that the planet can function in many of its most important roles without any need for shoreline, city, or crowd. It is a demonstration that large parts of the world operate all the time far from our direct experience. Yet those operations support the conditions under which our lives unfold. For someone listening in a quiet room, perhaps getting ready for sleep, this realization can be soothing. It shifts the focus from the idea of threat to the idea of support. The deep sea under Point Nemo is not a lurking danger. It is a reservoir of stability. It helps store carbon, buffer climate, recycle nutrients, and host diverse life, all while being so distant and so calm that most days we never think about it. Knowing that such a place exists and that it continues its work, whether we are busy, resting, or dreaming, can feel like discovering an underlying reassurance in the structure of the world. The stories and science together reveal that the ocean's center does not need drama to matter. Its true character is a balance of quiet motion, long memory, and soft connection to everywhere else. Currents that pass beneath it will eventually emerge elsewhere. Animals that live there are part of food webs extending to coasts and surfaces. Sediments that slowly accumulate there record climate variations that once played out in the air we breathe. In this way, the nothing in the middle of the ocean turns out to be a gentle concentration of many somethings, layered so deeply and moving so slowly that only a calm gaze can appreciate them. As this chapter closes, you can let the image of Point Nemo settle. A small dot on a wide map, an enormous column of water and time beneath it, and a quiet seafloor carrying traces of both the planet's earliest seas and our newest machines. The center of the ocean is still out there, solitary and complete, doing what it has done for ages. It hides nothing that wishes to leap out, only ongoing processes that are perfectly content to remain unnoticed. That knowledge can sit in the background of your thoughts like a deep, steady breath, one that you can match with your own as you drift toward rest. A lanternfish at Point Nemo, the smallest answer to a vast question. To understand what really lives in the dead center of the ocean, it can help to stop thinking in terms of the whole basin and focus, for a while, on a single small fish. In the midwaters beneath Point Nemo, one of the most common inhabitants is an animal hardly longer than a finger, a lanternfish. There are many species, but they share basic traits: soft, silver bodies, large eyes adapted to low light, and rows of tiny light organs along their sides and bellies. Individually, they are unremarkable. Collectively, they form one of the largest vertebrate biomasses on Earth. Somewhere under the remote coordinate we call Point Nemo, a lanternfish lives out its days in a world that never sees land, never knows a coastline, and never experiences sunrise the way we do. For this lanternfish, the day begins not at dawn, but deeper down in the twilight zone. During what we call daytime, it stays hundreds of meters below the surface, in water that is dim enough that only a faint bluish glow filters down from above. The temperature here is cooler than at the surface, the currents gentle and slow. Around it swim others of its kind, each maintaining its own small distance, all part of a loosely linked layer that stretches over enormous horizontal distances. The lanternfish's eyes are tuned to catch the last scraps of light, and to pick out any moving shadow that might signal danger or food. Its own body is marked with photophores, small organs that can emit light when needed. But for most of the day, these remain dim or dark, saving energy and avoiding drawing attention. Food does not arrive in abundance. Tiny planktonic animals drift by. Copepods, small crustacean larvae, fragile gelatinous forms. Threads of marine snow fall from the surface, each flake a small package of carbon, protein, and minerals composed of dead plankton cells, bacteria, and other microscopic debris. The lanternfish snatches what it can with quick snaps of its mouth, conserving effort. Every movement is a calculation. In water where energy is limited, chasing after fast-moving prey would be wasteful most of the time. Instead, the fish relies on the slow drift of food toward it, turning slightly to intercept promising particles or small animals as they pass. As hours pass, the light from above changes almost imperceptibly. It is never bright at this depth, but the lanternfish senses the difference when the sun begins to sink toward the horizon it will never see. The bluish glow weakens further, and faint cues, changes in the angle and intensity of light, subtle shifts in temperature, trigger a deeply embedded routine. This is the signal to begin moving upward. The fish's muscles, built to be efficient rather than powerful, propel it slowly towards shallower waters. It is not alone. All around, in countless unseen places, other lanternfish and midwater animals are beginning the same ascent. Together, they form an immense, spreading layer that rises hundreds of meters during the hours around dusk. Nearer the surface, the water is fractionally warmer and richer in plankton. Here, after dark, the lanternfish finds more food than it can during the day. Tiny crustaceans, small fish larvae, and other zooplankton gather where the last traces of productivity are strongest. The lanternfish feeds, its eyes now adjusted to the faint starlight filtering down and to the occasional flash of bioluminescence from other creatures. If it needs to, it can use its own photophores, flickering them in patterns that help confuse predators or signal its presence to potential mates. The light it produces is soft, blue-green, barely visible a short distance away, and quickly swallowed by the dark. Nothing here resembles the bright, colorful displays of shallow coral reefs. Instead, light is used sparingly, like a whisper rather than a shout. Above, at the surface directly over Point Nemo, the ocean might look utterly calm. There is no sign on the water that billions of animals have risen to feed beneath. The horizon remains empty. The stars are unchanged. Yet the sea under that spot is briefly fuller of active lives, all following the same up and down pattern that has been repeated for generations. For the lanternfish, this nightly ascent is an inherited habit, guided by internal rhythms and environmental cues, unconnected to any awareness of geographic remoteness. It does not know that it lives under a point that humans find fascinating. It knows only that there is a time to rise and a time to fall. As night deepens, the risk of predation increases. Other fishes, squid and larger predators, patrol these upper layers, using their own senses, keen eyes, sensitive lateral lines, finely tuned noses, to detect movement. To reduce its chances of being seen, the lanternfish may use counter-illumination. By emitting a faint glow from its belly photophores that matches the light coming from above, it can erase its silhouette when viewed from below. To a predator looking up, it becomes less visible against the faintly brighter surface. This trick is not perfect, and many lanternfish are caught regardless. But it improves the odds enough that the adaptation persists through endless generations. After several hours of feeding, the lanternfish begins to move back down, along with its invisible neighbors. The timing is gradual rather than precise. Some individuals start earlier, some later, but by the time the sky above Point Nemo begins to brighten with a new day, most of the layer has retreated to safer depths. Here, in the dimmer light, visual predators from the surface have more difficulty detecting them. The fish returns to the deeper part of the twilight zone, where it will spend the daytime in relative safety, metabolism ticking over at a measured pace. Over the course of its life, the lanternfish repeats this vertical commute thousands of times. Each night it climbs, each day it sinks. In doing so, it participates in a planetary process, the biological carbon pump. By feeding near the surface and excreting waste at depth, it helps transport carbon from upper layers to deeper waters, where it can be stored for long periods. Its own body, when it eventually dies and sinks, will add to this downward flow, joining the marine snow that slowly makes its way to the seafloor. The lanternfish's personal story is small. Its ecological effect, multiplied by trillions of individuals across the world's oceans, is immense. Everything described here would be true for a lanternfish under many parts of the open ocean. What makes the one under Point Nemo special is not its biology, but its address. It lives in a water column where no land is nearby, where human eyes are rare, and where surface signs of life are minimal. Yet its existence, and the existence of others like it, shows that even in the most remote coordinate we can name, the sea still supports complex, repeating patterns of life. The fish does not know it is at the center of anything. The ocean does not mark that coordinate with a line. The concept exists only in our minds, while the lanternfish continues its steady migrations regardless. Thinking about this small animal can be quietly grounding. When you picture the dead center of the ocean now, you might no longer imagine a barren void. Instead, you may see in your mind's eye a small silver fish drifting in dim blue, rising at night with countless companions, turning its photophores on and off in gentle patterns, feeding on tiny drifting prey and descending again with slow, practiced motions. Around it, other creatures do the same, forming a living, moving fabric that no map can fully capture. The vastness of the basin narrows to the rhythm of one beating heart and one simple cycle: up, feed, down, rest. In that sense, what hides in the dead center of the ocean is not a grand, singular secret, but an ordinary life multiplied until it becomes extraordinary in scale. The lanternfish under Point Nemo will never know that we have given a name to the surface above it, nor that we tell stories about its home. It will simply continue, in darkness and calm, doing the small things that, together with countless others, help keep the ocean and the climate in balance. Holding that image in mind, you can let the idea of Point Nemo become less of a sharp point and more of a gentle pulse. One tiny fish swimming up and down beneath a very empty-looking spot on a map in a sea that is full.